Welcome to The Explainer. Today, we're diving straight into the incredible megastructures that silently guard our global supply chain. If you're a focused learner who really wants to understand exactly how the modern world functions behind the scenes, well, you are in the exact right place. We're going to break down these massive, highly specialized, and incredibly energy-intensive logistics hubs known as marine port cold storage facilities. So let's get right to it.
Think about it for a second. How do fresh bananas and vital vaccines survive a whole month at sea? It's kind of a relatable mystery, right? You stroll into your local grocery store and see perfect, unblemished fruit, or you head to the pharmacy to pick up a life-saving medication. But long before those perishable goods ever hit a truck on the highway, they have to transition from massive reefer vessels out on the ocean to our terrestrial distribution networks. Marine port cold stores are that critical interface. They're literally the high-tech, heavily guarded checkpoints standing right between the harsh, unpredictable environment of the sea and your local supermarket shelves.
Okay, here's our game plan for building the ultimate marine cold store from the outside in. We'll be covering 1. The global icebox. 2. Anatomy of the fortress. 3. The climate control zones. 4. The science of cold. And finally, 5. Choosing the right coolant. Starting us off, Section 1, the global icebox. Now you might be thinking a cold store is just a giant warehouse with a really big air conditioner slapped on the roof. But honestly, scratch that. These facilities do so much more than just store boxes in the dark. They are incredibly active nodes in the supply chain. Yes, obviously, they maintain temperatures to preserve the shelf life of cargo, but they also handle all the consolidation and deconsolidation. That means they are constantly breaking down these huge shipments from bulk reefer vessels or stripping standard shipping containers to repackage everything for local distribution. Plus, they provide dedicated, highly secure, temperature-controlled zones for customs and agricultural authorities to inspect organic cargo, which is an absolutely massive quarantine requirement. They even offer value-added services right on site, like prepping seafood with blast freezing and glazing the literal minute it lands at the port.
Moving right along to Section 2, Anatomy of the Fortress.
It's honestly fascinating to look at the building itself as this living, heavily armored organism. Building one of these requires a crazy integration of structural, mechanical, and electrical engineering. These fortresses are built using high-density polyurethane, or PUR, and polyisocyrenate, or PIR, sandwich panels. Think of these heavy-duty structural panels as the actual skin of the facility. They provide incredible thermal resistance, basically acting as a suit of armor against the outside heat. But arguably just as important, they act as a super strict vapor barrier. You absolutely have to prevent moisture from the humid port environment from sneaking in. Why? Because in a sub-zero facility, moisture means deadly icing, and icing will literally destroy your equipment and your cargo.
Okay, get this. This is how far engineers have to go to protect the building from its own extreme internal environment. We literally have to heat the floor beneath the giant freezer. It sounds completely backward, doesn't it? Spending money and energy to install glycol loops or electrical trace heating mats directly beneath a freezing facility? But if you don't do this, the freezing temperatures will eventually penetrate the ground below, causing the earth to freeze, expand, and create what is known as structural heave. Without a heated subfloor, the expanding frozen earth would literally rip the entire megastructure apart from the bottom up. No way around it.
Every fortress needs a nervous system, right? Down at the docking bays, which are essential at a busy port, they use these clever, inflatable dock shelters to maintain a perfect environmental seal between the cold store and the delivery trucks. But the electrical requirements here are just mind-blowing. We are talking about massive power needs, mostly for giant compressor motors, which use specialized substations and variable frequency drives. Because the stakes are so high, having 100% generator backup is totally mandatory to prevent a catastrophic total loss of cargo if the grid fails. Managing all of this is the SCADA network and the building management system. This is the brain of the operation, continuously monitoring thousands of temperature sensors, managing defrost cycles, and instantly triggering alarms for leaks. Even the lighting is highly specialized. We're talking high-efficacy, ultra-low heat LED fixtures rated IP65+, just so they can survive the sub-zero high-moisture environment.
All right, let's jump into Section 3, the climate control zones. So, a marine cold storm is not just one giant room set to one uniform temperature. It's meticulously zoned based on exactly what cargo is inside. At the top end, we have chillers or coolers. These are kept between +2 and +10 degrees Celsius, and this is where your fresh produce, dairy, and pharmaceuticals hang out. Step down a level, and you enter the freezers. These are held between -18 and -25 degrees Celsius, strictly for frozen meat, poultry, and processed foods. But that bottom row? That is where the magic happens. Blast freezers. These operate at a punishing -35 to -40 degrees Celsius. They aren't just cold rooms. They use incredibly high-velocity airflow to freeze fresh products rapidly. And the why is important here. Super-fast freezing minimizes the formation of ice crystals, which completely preserves the cellular integrity of freshly landed seafood.
And this brilliantly answers that relatable mystery from the very beginning of the explainer. If you're importing fruit like apples or bananas, just controlling the temperature isn't enough. Controlled atmosphere, or CA, rooms literally put the fruit into suspended animation. They don't just chill the air, they precisely regulate the levels of oxygen, carbon dioxide, and nitrogen. By literally starving everyday fruits of certain gases, the CA rooms entirely suspend their biological ripening process. This is the only way to ensure a banana doesn't turn brown before it even leaves the port.
Which brings us to Section 4, the science of cold.
So how do they actually make it cold? Most marine cold stores operate on the standard vapor compression refrigeration cycle. It's basically a continuous thermodynamic loop that absorbs heat from inside the cold room and violently rejects it outside. It starts with stage 1, evaporation inside the cold room, where warm air blows across coils filled with low-pressure liquid refrigerant. The refrigerant absorbs the heat, boils into a gas, and cools the room air. Stage 2 is compression in the plant room. Here, a massive compressor mechanically squeezes this gas, which drastically spikes its pressure and temperature. Then we hit stage 3, condensation up on the roof, where ambient outside air cools the hot gas, condensing it back into a high-pressure liquid and dumping that absorbed heat into the atmosphere. And finally, stage 4, expansion. The high-pressure liquid hits the expansion valve. This is the crucial moment. This valve acts as a physical bottleneck, forcing a massive, sudden drop in pressure. This pressure drop causes the liquid to cool down rapidly, prepping it to enter the evaporator and restart this incredible thermodynamic heartbeat all over again.
And finally, Section 5, choosing the right coolant.
Large-scale port facilities actually face a severe engineering dilemma when choosing what refrigerant to pump through their veins. On one side, you have ammonia, also known in the industry as R717. This is the absolute gold standard for massive marine cold stores. It is highly thermodynamically efficient, has zero ozone depletion potential, and zero global warming potential, or GWP. Sounds perfect, right? But the catch is that it is toxic and slightly flammable, which means it requires rigorous, expensive safety standards like dedicated leak detection, extreme ventilation, and special ATX-rated explosion-proof electrical equipment. On the other side, you have Freon, or HFC systems. These are often used for smaller zones because they are totally non-toxic and much safer for humans to be around. However, they are currently being phased down globally because they have a notoriously high global warming potential. So it's this constant, high-stakes balancing act between thermodynamic perfection and environmental safety versus immediate, on-site human safety.
So how in the world do engineers safely use highly efficient but undeniably toxic ammonia in a facility packed to the brim with valuable food and busy workers? While smaller facilities might use a DX or direct expansion system where the refrigerant circulates directly into the cold room evaporators. But massive port facilities, they completely bypass the danger by using what's called a secondary loop system. In this setup, the primary, potentially hazardous ammonia plant is locked safely away in a highly restricted mechanical room. In there, the ammonia is just used to cool a totally harmless secondary fluid, typically chilled glycol or brine. That safe chilled glycol is what actually gets pumped out into the cold storage rooms, where the cargo and the staff are. It's a brilliant workaround. It keeps the hazardous chemicals entirely restricted to the plant room while still delivering the massive freezing power required to run the warehouse.
So, we've built a fortress, powered its nervous system, zoned its climates, and pumped its veins with sub-zero coolants. But I want to leave you with a provocative question to think about. What really is the hidden energy cost of keeping our globalized diet fresh? These massive, invisible, energy-intensive megastructures are literally the only reason we can eat fresh produce totally out of season, or easily access sensitive global medicine at our local pharmacy. Understanding the absolutely massive thermodynamic effort required to maintain this cold chain makes you look at a simple piece of fresh fruit in the dead of winter in a completely different light, doesn't it? Thank you so much for joining me on this explainer. Keep learning, stay curious, and I'll see you next time.